We had discussed at the beginning of the course that when you have a macroscopic system, that you have only very limited information. You know some macroscopic properties, maybe the number of particles contained, maybe the total energy of the system, maybe total magnetization of the system, but just a handful, typically just a handful of properties, and these are your macroscopic data. And the challenge, we had said, was to make predictions about the system, to infer interesting physical properties of the system using only these macroscopic data. And the challenge is how to process this macroscopic data mathematically. How do you encode the information that you have about the system mathematically? And to approach that more systematically, I would like to distinguish between three different types of macroscopic data. Macroscopic data typically comes in one of three forms. One possibility is that you have external fields. Say the system that you investigate is a magnet, and you apply an external magnetic field to it. And then you can control this external field. This is a macroscopic information that you have about the system, that it's subject to this external field. An external field is an example for a more sort of a general class of parameters or macroscopic variables that you can have that are called control parameters, that are parameters of the system that you can control externally. Another example could be the volume of your system. The system is in a container. You can vary the volume of the container, and so the volume is a control parameter. So you have external fields or other so-called control parameters. Another type of macroscopic information that you might have are constraints, and they are sharp constraints in the sense that there is no uncertainty about these constraints. The constraints are not given in the form of an expectation value. We'll come to that in a minute. That's the third type. But you have a given sharp value for a certain physical quantity, a certain physical observable. For example, the number of particles. You have in a container, again, you have, say, a gas, and there is no exchange of particles with the outside. The number of particles is fixed, and it may happen that you know that you are given the number of particles inside your container. Or you have, again, a magnet that's composed of many elementary magnets, say spins in a lattice, and the number of these elementary magnets is given, and it doesn't vary. Of course, in practice, also in those cases, there will be some uncertainty. When you have a gas in a container, you cannot possibly count the number of atoms or molecules in your container. So it will be given within some finite measurement in accuracy. But it's different from the scenario where you have a system that can exchange heat, say with the environment, and you are given the average energy or the expected value, the expectation value of the energy of the system, but it cannot possibly be a sharp value because the system exchanges energy with the outside. So this is the case, the second type where you have sharp constraints. And then finally, the case that I had already alluded to is that you are given information in the form of expectation values or averages. And with each of these three types of macroscopic data, we have to deal differently. So we can ask in all three cases how we should account for these data mathematically. In the first case, when we have a control parameter, this means mathematically that some or all relevant observables that you have in the system, in particular the Hamiltonian, will have an explicit dependence on your control parameter. So this manifests itself in an explicit parameter dependence of some or all relevant observables. Let me call the relevant observables AI, and they get now a dependence on the control parameter, which I call Xi. Consider as an example, I already mentioned the case where you have a magnet that is subject to an external magnetic field. Now, for a magnet, as for practically all systems that we will consider, the energy and hence the Hamilton operator is always amongst the relevant observables. So let's take that as the starting point, that the Hamiltonian and therefore the energy is a relevant observable. And let's take the case of the magnet, where we subject it to an external magnetic field. And now the Hamiltonian of the magnet depends on the external magnetic field. I'm sure you studied that in quantum mechanics, cases where you have a system with a magnetic moment subject to external magnetic field. You have a field-dependent Hamiltonian. So this Hamiltonian will depend on the external magnetic field, B, and therefore you get the Hamilton operator as a function of B. So in this case, the relevant observable is the Hamiltonian, and the external control parameter, the external field, is B. So this is how you account for these external parameters, type 1. What about the type 2 macroscopic data, where you are given sharp constraints? In that case, the way you account for that mathematically is in your choice of Hilbert space. Well, you know, we're doing all of this quantum mechanically from the start. If this were classical, then this would manifest itself in the choice of phase space. But here we're talking quantum mechanics, so it's reflected in your choice of Hilbert space, or a subspace of Hilbert space, or a subspace thereof. Again, an example. I mentioned that one sharp constraint that you might have could be the number of particles in your system. So let's consider this as a first example where you have a sharp value for the number of particles. Say you have n particles. This is a sharp value. And then you account for that by describing your system in an n-particle Hilbert space. It could also be, as a second example, that you have a system which is completely isolated, no form of energy exchange with the outside world, perfectly isolated, so the energy of your system is perfectly conserved, and you are given the energy of the system as a sharp constraint. Again, you have to take this with a grain of salt. It's always within a certain measurement accuracy, but in principle it's given as a sharp value. So example number 2, sharp value for energy. In that case, how do you account for that? Well, in general, when you are given macroscopic data, you have many possible microstates, which in the quantum case are pure states, that are compatible with your macroscopic data. We had discussed it at the beginning, that this is the basic problem, that you have to work then with not a specific microstate, but you have a probability distribution over many possible microstates. Now, if you're given an energy constraint, then essentially you restrict the set of allowed microstates to all those microstates whose energy lies within the given range. Yeah? So you have a sharp value for the energy plus minus some measurement uncertainty, and all the microstates that are allowed, that are part of your statistical mixture, must have an energy within this energy range. And hence, in your Hilbert space, you restrict your microstates to a subspace of Hilbert space, and the subspace that's the space that is spanned by all the microstates whose energy lies within this allowed range. So you describe your system in a subspace of Hilbert space, which is spanned by all the microstates that satisfy the energy constraint. And so this is how you account for the type 2 macroscopic data. And then comes the most interesting type of macroscopic information. That's when you are given expectation values or averages. Well, basically the first two constraints, they fix the Hilbert space that you work in, and they fix the possible parameter dependence of your relevant observables. And now you are given expectation values for your relevant observables. The state of your system, that's what we had discussed last week. The state of your system is going to be described by some density matrix. And that's the most general form of a physical state. And since we don't know precisely which microstate the system is in, this is certainly not going to be a pure state, but it's going to be a mixed state. We have to work with the density matrix. And we are faced with the problem that we have to choose a suitable density matrix that takes into account all our macroscopic information. Now, what shall we do if the macroscopic information is given in the form of expectation values? So you have several relevant observables, AI, and you know that whatever state you choose, whatever density matrix row you choose, it must give a certain expectation value for these relevant observables. But of course there are many possible density matrices that all give the same expectation values for your relevant observables. So to make it specific, think once again about a system where the energy is a relevant observable, but the system is not isolated. The system is in contact with the outside world. It can exchange heat. And as a consequence, the energy is known only on average, only as an expectation value. You want to choose a density matrix that reproduces this expectation value, that gives the correct expectation value for the energy, expectation value of the Hamiltonian. This is just one number, this one expectation value. But of course, if you have a large system, you have a density matrix in a very high dimensional Hilbert space, the density matrix has many, many degrees of freedom, and you have only a single constraint. So there is a vast number of density matrices that all give the same expectation value for the Hamiltonian. So which one do you choose? And here enters perhaps the most profound and the most fundamental idea of statistical mechanics. We need a criterion for choosing the density matrix. Which criterion do we choose? Last week we had talked about information about the microstate, or the lack of information about the microstate. And we had found that this is described quantitatively by the entropy. That's precisely what the entropy means physically. Entropy is a measure for our ignorance about the microstate. When we choose a density matrix with a high entropy, then this means we know little about the microstate. If we choose a density matrix with a low entropy, this means we claim we know a lot about the microstate. In this scenario here, all we know about the system are these macroscopic data. We don't know anything beyond that. So of all the allowed density matrices that give the right expectation values, we should choose the one that has the highest entropy while satisfying this constraint. Why? Because if we chose any other density matrix, then we would claim to know more about the microstate than the macroscopic data tell us. So choosing the state, the density matrix with the highest entropy, that is still, whilst it is still compatible with the macroscopic data, reflects the fact that into our density matrix we don't put any more information than what is given to us in the form of macroscopic data. Some people say it's the least biased choice of the density matrix. That if you choose any other density matrix, then you would introduce a bias about the microstate. And so the principle here is also called the maximum entropy principle. It says, choose that state, i.e. density matrix rho, which carries the least information about the microstate, while still being compatible with the macroscopic data that you are given. So it should still reproduce the correct expectation value that you are given as macroscopic data. But under this constraint, it maximizes the entropy and hence minimizes the information it carries about the microstate. Okay, so this is the fundamental principle. From here we can essentially construct and derive all of statistical mechanics. That's the basic idea. So you're given incomplete information in the form of this macroscopic data. You have to pick a state, a density matrix. You have to describe the system by some density matrix. that is compatible with this macroscopic data. There are lots of possibilities, and the one you pick is the one with the highest entropy, compatible with the constraints. And the basic idea is that you say, if you picked any other density matrix, it would have a lower entropy. Lower entropy would mean it would contain more information about the microstate. But this is information which is not warranted by the macroscopic data. It would be information that goes beyond the macroscopic data that you are given. And this is, there's no justification for doing that, because you don't have extra information. The macroscopic data is all you have. So into your density matrix, you shouldn't put more information than the macroscopic data. I made a lot of words and I talked a lot about this because it's so important, and I want to make sure that you got the basic idea. Because we'll see that in action, and you will see how from this principle basically all of statistical mechanics will follow. Well, one relevant observable that is basically always amongst your set of relevant observables is the Hamilton operator, because the energy is always amongst the macroscopic physical observables that are given in one form or the other, either as a sharp constraint or as an expectation value. So let us consider the case where the energy is given to you in the form of an expectation value. So the expectation value of the Hamiltonian. And this should be the only expectation value that is given to you. So let's say there are no further expectation values given. Then I claim that the following density matrix, rho, which has the following form, 1 over z times e to the minus beta times Hamiltonian, where z is the trace of e to the minus beta Hamiltonian. I claim that this density matrix is the unique density matrix that gives the correct expectation value for the Hamiltonian and at the same time maximizes the entropy. So that amongst all density matrices that give the given expectation value for the Hamiltonian is the one with the maximum entropy. Let's try to check that. Remember, the entropy of a density matrix, that's minus Boltzmann constant trace rho log rho. When I insert the state that I wrote above, then I have this exponential form. So when I take the logarithm, the logarithm of the exponential, then I get a minus beta h. So when you do that, you find that the entropy of this particular state is given by k log z plus k beta times the expectation value of the Hamiltonian in the state rho, in that state rho that I wrote down above. Now let's take another mixed state that gives the same expectation value for the Hamiltonian. So let's take another mixed state rho prime, different from rho, that gives the same expectation value for the energy. So the expectation value of the Hamiltonian in rho primed equals the expectation value of the Hamiltonian in rho. This alternative state, rho primed, has an entropy S of rho primed. Now let's consider the difference between the two entropies. Let's consider the difference S of rho minus S of rho primed. Let me start with S of rho primed. S of rho primed is again minus k trace rho primed log rho primed. Since we are subtracting it, gets a positive sign, and I write it as the first term. It's k trace rho primed log rho primed. And then we have the entropy of rho, and for that I use the form above, that this is k log z plus k beta times the expectation value of the Hamiltonian in the state rho. But I said that the expectation value of the Hamiltonian in rho is the same as the expectation value of the Hamiltonian in rho primed. Both states give the same expectation value for the energy, so I can replace rho by rho primed. And then you can convince yourself that what I just underbraced, that this is the same as minus k, the trace of rho primed log rho. Just take the form of rho above, insert it into this blue formula. When you take the logarithm, you get a minus log of z. And so that gives you, with the minus in front, it gives you the k log z. And then you get minus beta h, expectation value in rho primed. And this is combined with the minus k in front. This gives you the k beta expectation value of h in rho primed. So you have, for the difference of entropies, I have a k in front, and then I have trace rho primed log rho primed minus trace rho primed log rho. This is an expression that you should have seen on your last problem set. It's the quantum version of relative entropy. This is the relative entropy of rho primed and rho. And I told you on the last problem set that the relative entropy of two density matrices is always larger or equal to 0. This is never negative. In other words, and this is the difference of the two entropies. In other words, this tells you that the entropy of rho is always larger or equal the entropy of rho primed, whatever rho primed is. There is equality, so this is equal to 0 if and only if rho primed equals rho. This is another property that I mentioned to you on the last problem set. So in fact, rho, the state above, is the unique state that maximizes the entropy at a given expectation value for the energy. This is what makes this state here so special. So the conclusion is that among all states with a given expectation value for the energy, the rho above is the unique state that maximizes the entropy. This is why it is so important, and this is the state that we should use. This is our maximum entropy principle. Yeah? The state in the box above is the one that we must use if all we know macroscopically about the system is the expectation value of energy. And this state has a special name. It's in the title, it's the Boltzmann-Gibbs state, or sometimes also called the canonical state. We can generalize our result and now consider the case where we are given several expectation values. We can formulate this very generally. We can say that we are given expectation values of certain observables which are relevant, AI, and these may furthermore depend on a control parameter. So we also take into account the possible type 1 macroscopic data that we have a dependence on a control parameter. So the AI are really an arbitrary set of observables that are relevant for the problem at hand. And they may or may not commute with each other. So it's not necessary that they commute. And they possibly depend on a control parameter, or even several control parameters. And now, as in the case of the Boltzmann-Gibbs state, where only the expectation value of the Hamiltonian was given, we seek the density matrix, we seek the state that under these given constraints maximizes the entropy. And I'm not going to give the mathematical proof here, I'm just going to state that the density matrix that results, the unique density matrix that maximizes the entropy, has a form that is very similar to the Boltzmann-Gibbs form that we just saw. It's 1 over z, and then an exponential e to the minus, and then we sum over all I, sum over all the relevant observables that we have in our set, and then we have some parameter lambda I times the operator AI, which may depend on psi, where the z is a function of the lambdas and psi, is given by the trace of this exponential, e to the minus sum over I lambda I AI of psi. It has exactly the same structure as before. The z, of course, you can immediately see that this density matrix is correctly normalized in the sense that the trace of rho is 1. Because when you take the trace of rho, then you have the trace of the exponential divided by z, but z itself is the trace of the exponential. So you divide the trace of the exponential by the trace of the exponential. This is obviously equal to 1. So clearly the z has the purpose that it guarantees the normalization of your density matrix. Now this z here will appear over and over again. It's a very fundamental object in statistical mechanics. This is called the partition function. And it ensures, as I said, it ensures that the trace of rho is equal to 1. The lambdas that appear in the exponential, these are the so-called Lagrange parameters associated with the relevant observables, AI. So these are the Lagrange parameters. The reason for this terminology is that you can derive this form for the density matrix. Well, this is an example. When you seek the density matrix that maximizes the entropy under given constraints, this is an example for a variational problem. It's an extremization problem under given constraints. And perhaps you've seen that in mathematics or in other contexts, that you can achieve that by introducing so-called Lagrange parameters or Lagrange multipliers. That's where this comes from. So here we have the most general form of the density matrix for a macroscopic system when you are given an arbitrary set of expectation values as a constraint.